Alright, some of you may have noticed that my first video for section 14.2 had some sort of error where it stopped following along with me, so I'm going to try again. Um, so this section is about factor groups from normal subgroups, which is a different way to get at factor groups using just the normal subgroup property that we defined last section. So let's recall what it means to be a normal subgroup. So a subgroup H of a group G is called normal if the left coset containing A is equal to the right coset containing A for all A in G. So the theorem is that we can define, this is all we need to define coset multiplication. And actually, if coset multiplication is defined, then the subgroup has to be normal. So let's let H be a subgroup of G. Then left coset multiplication defined by AH times BH is equal to A to BH, as in the previous video, is well defined if and only if H is a normal subgroup of G. Okay, so let's prove this statement. So I'm going to prove most of it, and I'll leave some of the details to homework. But first, let's suppose that AH times BH equals ABH is well defined. We want to show that H is normal. That is, that AH equals HA for any A. G. We'll do this by showing that AH is contained in HA and that HA is contained in AH. Actually, I'm going to leave this one for homework. So we'll show the first containment. So let's let A and G, and suppose X is in the left coset containing A. Well, then we can choose representatives of that coset to be X and A inverse in AH. So we have, I'm sorry, A inverse should not be in there. X in AH and A inverse in A inverse H. So we get that XH times A inverse H, because this multiplication is well defined, we should get X A inverse H. But choosing representatives A in AH as a representative gives us that A times H times A inverse H is equal to A inverse H, which is, of course, EH, and EH is just H. So, since X and A are in the same coset, these sets are equal. These sets are clearly equal. This means that we get XA inverse H is equal to H. So this says that XA inverse is equal to some little h, since these cosets over here are equal. Hence, x is equal to HA by multiplying on the right by A on both sides, which means that x is in HA. Since x was arbitrary, we have that AH is contained in HA. So, as you'll show that HA is contained in AH from the homework. So we get that AH equals HA. So H is a normal subgroup of G. So that proves one direction of the statement, but it's an if and only if statement. So now we need to show the other direction. Okay. So let's suppose this is going to be similar to the proof in the previous lecture. So suppose H is a normal subgroup of the group G. We need to show that AH times BH is well defined, i.e. that it's we get the same result regardless of which elements from the coset we choose. So choosing the obvious representatives, A in AH and B in BH, we get AH times BH equals ABH. Suppose we choose instead AH1 in AH and BH2 in BH, then AH1H is the same thing as AH, and BH2 is the same thing as BH, but we get this thing on the right-hand side, AH1 BH2 times H, which may not be the same thing as ABH. So we need to show that, and it follows from the fact that H is normal. So since H is normal, I'm going to use this for B, BH equals HB, so H1B is equal to BH3 for some H3 in H. Thus, AH1 BH2 times H is the same thing as ABH3 using replacing this with this times H2 times H, which is the elements of H just permute this, so this does live inside AB. So since ABH3H2 is in AB times H, we conclude that we have ABH3H2H is equal to AB times H, and multiplication is well defined. That proves this theorem. Okay, so Now that we know that multiplication is well defined for normal subgroups, we can get the following corollary, which is really what we're after here, which is that if H is a normal subgroup of G, then the cosets of H which of course is denoted G mod H, form a group under the operation AH times BH equals AB times H. So the proof is simply checking the group axioms. So first, associativity. This is going to follow from the fact that the product in G is already associative, but let's run through the argument. So we want to see that if I do AH times BH and then do multiplication by CH, I should get the same as if I had the parentheses or the brackets moved around. So here I would get ABH, the parentheses are going to get a little bit cumbersome here, times CH, which gives me AB times C times H. But now, since multiplication in the group itself is associative, I can reassociate this product right here, and I get bracket A times BC, close bracket H. And now if I just re-expand that, what do I get? I would get AH times BCH, which is AH times bracket BH times CH. So associativity holds. Now let's check that there's an identity element. So let E be the identity element in G. Then if we do AH times EH, what we get is AEH, which is AH. So it seems to work on the right-hand side. And if we do it in reverse order, we get a similar computation. AEH equals AH. Thus, EH, which is just the subgroup H, is the identity element for G mod H. Lastly, we need to check that every element has an inverse. So check that inverses exist. So let A in G. Then if we do AH times A inverse H, we get A inverse H, which is EH, which is the identity element in G mod H. And if we do it in reverse order, we get the same thing. Thus, the inverse of AH is A inverse H. So all group properties hold. So G mod H is a group. That proves this corollary. So now we can define factor groups using only normal subgroups. So the definition is that if H is a normal subgroup of G, then the group G mod H is called the factor group, or quotient group, probably less frequently, of G by H. And I want to put a warning in here. The normal part is extremely important. So we actually showed above that this is only going to work if the group is normal. So warning, if H is not normal, multiplication is not well defined. Of cosets is not well defined. So G mod H is not a group. So normality is a big part of what we're doing here. So let's do an example. Let's let G be Z. So since Z is abelian, every subgroup is normal. So we don't have to worry about checking this normality condition. So let's redo the example from the previous video. So 3Z is a normal subgroup of Z. And thus, we can form the factor group Z mod 3Z without reference to a homomorphism. And now we can do computations using the easy version. So for example, 1 plus 3Z plus 2 plus 3Z. Well, now we know how that's going to be computed. That's combining 1 and 2 and adding that to the subgroup, which is 0 plus 3Z. Which is 3, of course, plus 3Z. But this is the same thing as just 3Z. So note that we could have described 3Z instead as writing it as the cyclic group generated by 3. So Z mod 3Z is the same thing as Z mod 3, and those are both isomorphic to our old friend cyclic group with 3 elements. So let's return to another example from way back at the beginning of class, maybe first week of classes. Let's let G be R under addition. Then the cyclic group generated by 2 pi is, of course, the set negative 4 pi, negative 2 pi, 0, 2 pi, 4 pi, etc. And each coset of 2 pi has exactly one element, x, such that 0 is less than or equal to x is less than 2 pi. So the cosets R mod cyclic group generated by 2 pi are in bijection with the interval 0 to 2 pi, and if we add things, so I'll do a specific example. If we add, say, 5 pi over 4 plus 2 pi plus, let's say just pi plus 2 pi, we get 9 pi over 4 plus 2 pi, which is the same thing as just pi over 4 plus 2 pi, subtracting 2 pi from 9 pi over 4. So we see that this factor group, R mod 2 pi, is isomorphic to our set R sub 2 pi with addition modulo 2 pi, way back from before. Okay, so this concludes this video, so why don't you go in and do some practice problems about factor groups that arise from normal subgroups. Thanks for your time.